Okay, I think it's 10:30. So before we start, someone pointed out that I have my hint in problem 1A is incorrect, right? Assignment 2, problem 1A, I say hint, differentiate the Killing equation. You don't have to differentiate the Killing equation in 1A. You just use the Killing equation and the fact that DH is 0, and it's trivial. In 1C, you will have to differentiate the Killing equation. So I put my hint in the wrong place. I think I said it twice. Anyway, and I think the assignment is due a week from yesterday, right? And it's all on Jacobi fields and curvature and Jacobi fields, chapters 4 and 5. So we started talking about completeness, right? We said what it means for a Riemannian metric to be geodesically complete. That means given any point, if you look at the exponential map at that point, it's defined on the whole tangent space at that point. In other words, you can follow geodesics. Any geodesic with initial point P and initial velocity V is defined for all time. Right? Not all Riemannian metrics have that property. That's called geodesically complete until halfway through this lecture when we'll see that it's equivalent to complete. And we also showed that on a Riemannian manifold, you can get a distance function, let's say on a connected Riemannian manifold, by just looking at the infimum of the lengths of any piecewise smooth curve joining those 2 points. That gives you a metric space distance function. And therefore, you get a topology because it's a metric space, and that coincides with the original topology. Okay, so today we're going to prove the Hopf-Rhino theorem, but before we do that, we have the following important proposition. Suppose M is geodesically complete. As I said, that means that the geodesics exist for all time, all of them. So that means that for all P and M, XP is defined on all of TPM. Then, given any point, any P and Q and M, there exists a minimizing geodesic from P to Q. And note, this need not be unique. This is not in general unique. And from our trusty friend, the sphere, we already see an example of that because we know what all the geodesics are on the sphere, and we know they're defined for all time. You just keep going round and round the great circle, right? So that's geodesically complete. And we know that if you have antipodal points, there's not a unique minimizing geodesic joining antipodal points, right? There's infinitely many. So this is not unique in general. Okay, so let's prove this. Let's let L be the distance from P to Q. I mean, we might as well assume that P is not equal to Q, right? Because if P equals Q, the constant curve is a geodesic joining P to Q. So this is some positive. If P equals Q, there's nothing to do. This is some positive number. Let B delta P be a normal ball centered at P. And let S delta P be the boundary, be the geodesic sphere. Okay, so so note S delta P is compact, right? That's because S delta P is the image of the boundary of the ball of radius delta in TPM, and that's just a normed vector space, right? It's an inner product. It's an inner product space, finite dimensional inner product space. So we know that closed balls are or the boundary of a closed ball, that's a closed and bounded set. It's compact, and this is the continuous image of a compact set. Continuous image of a compact set. Okay, so the geodesic spheres are compact, and hence the map x goes to the distance from Q to x is continuous. So it attains a global min on S. Right, because we proved at the end of last lecture that the distance function to a point is a continuous function. Well, that's because this is a metric space. And so if I restrict a continuous function to a compact set, we know that it attains a global min. So there exists some x naught in this geodesic sphere such that the distance from x naught to Q is less than or equal to the distance from x to Q for all x in this sphere. Okay, so I'm going to draw a picture, and I'm going to try to keep that picture on the board for the whole proof. So this is the point P, and then this is S delta of P, and the point Q is, we can assume that Q is not inside this geodesic ball, in this normal ball, because if it was, we know there's a geodesic joining it, right? So I've drawn Q outside. So there's some point x naught so that the distance from Q to x naught is less than or equal to the distance from Q to x for any other x on here. Okay, so notice x naught need not be unique. And again, we can find an example by looking at the sphere. If I start here and I take some normal ball, and let's say I take the antipodal point again, how many points on this geodesic sphere are closest to that point? They're all the same distance. Okay. So in this picture, this looks like this is the only point. This is the only point on this orange circle closest to that, right? But there, in general, you could have more than one. Okay, and the idea now is we know there's a geodesic here going through here, and we're going and the hypothesis is that all the geodesics exist for all time. We're going to show that this geodesic actually hits Q. Okay, and then we'll be done. Well, and then show that the length of it is Q. So so x naught is equal to, let me not write it over here. I want to keep the picture for the whole proof. X naught is on the geodesic sphere, so it's xp delta v for some v in TPM with length 1, right? Because it's the image under xp of some vector in TPM with length delta. Right? So I can write it like this. And let's consider the geodesic gamma v of t, which is xp of tv. So by hypothesis, this is defined for all time. This is where we use the geodesic completeness. Okay, so we'll show that gamma, let's just call this gamma, so I don't keep writing gamma sub v. We'll show that gamma of L equals Q. This will complete the proof because that means that this is a geodesic. It goes through P, right? Gamma of 0 is P, and gamma of L is Q. So it's a geodesic joining P to Q. and it has length L. So this is unit speed because V is a unit vector. This is a normalized geodesic. The initial velocity of this is V, and V has length 1. So this is a unit speed geodesic, and therefore Q appears at the parameter L. That means the distance from P to Q is L. So gamma is a geodesic joining P to Q with length L, which is the distance from P to Q. Okay, so that would complete the proof. So we're reduced to showing this. Let's define a subset A of the closed bounded interval from 0 to L to be all those points T, such that the distance from gamma of T to Q is L minus T. Okay, so we know that 0 is in A because gamma of 0 is P. So we get D of gamma 0 Q is D of PQ, which is L minus 0. Okay, so A is not empty. Moreover, since both gamma and D are continuous, A is closed. Right? Because if I look at a sequence of T's in here converging to some limit, then by the continuity of gamma and T, this will hold at the limit as well. Okay, so I have a non-empty subset of 0, 1, and it's closed. So hence, the supremum of A is contained in A because A is closed. Okay, so we claim that the supremum of A is L. If this is true, this implies that L is in A. The supremum of A is in A because A is closed. So if we can show the supremum is L, that means L is in A, and that means that the distance from gamma L to Q is L minus L, which is 0, and that means gamma of L has to be Q because it's a metric space. Okay, so we need to now, we've reduced it to showing that the supremum of this set is L. And we know the supremum is less than or equal to L, right? Because everything in A is less than or equal to L. So we just have to show that it can't be less than L. So we need to show that supremum of A is not less than L. So let's let T naught be in A with T naught less than L. We need to show that there exists some delta prime such that T naught plus delta prime is in A, because this implies that T naught is not the supremum of A, right? For anything less than L, I'm going to find something slightly bigger, which is still in A. So anything less than L can't be the supremum of A. All right, so how are we going to do this? Let's let B delta prime at gamma of T naught be a normal ball at gamma of T naught with S delta prime, let's just call it S prime, be the boundary So luckily I still have my picture here. I'm following this this curve gamma, I have some point gamma of T naught, where T naught is strictly less than L. And I'm looking at the ball S prime, which is S delta prime gamma of T naught. So we're going to do again what we just did with the first geodesic ball. We're going to look at the point on that geodesic sphere, which minimizes the distance to Q, or a point. Let X naught prime be a point on S prime where the distance to Q for X in S prime has a minimum, global min. So in the picture, right, clearly that's going to be here. But let's use the picture just to guide us. Let's pretend it's here. Okay, this is the point on this orange geodesic sphere that's closest to Q, or up point. There might be more than one again. So it need not be unique. Okay. So what do we know? The distance from gamma of T naught to Q is L minus T naught, since T naught is in A. That was the definition of this set A. Let's call this equation 1. Also, the distance from gamma T naught to Q is equal to delta prime plus the minimum over all X in S prime of the distance from X to Q. And that's equal to delta prime plus the distance from X naught prime to Q. And this is because any curve from Q to gamma of T naught must pass through S prime. Okay, so if I go back to the picture, right, we're saying that the distance from this point to here, well, this is if you look at any curve between these 2 points, then this curve has distance at least delta, because we know that the length, the distance from a point on the geodesic sphere to the center is delta prime, right? Delta prime. So this yellow curve has length at least delta, and this is a curve from Q to a point on this orange sphere, and we know that those have length. The smallest length is the one where the point is X naught prime. Okay, so this is equation 2. Now let's combine 1 and 2. I've erased the definition of A, unfortunately, but what can you do? Combining 1 and 2, we get L minus T naught is this guy, which is equal to this guy. Delta prime plus D of X naught prime Q. And I'm going to call this 3. Okay, so by 3 and the triangle inequality, what do we get? The distance from P to X naught prime is greater than or equal to the distance from P to Q minus the distance from Q to X naught prime. That's just the triangle inequality rearranged. And that, this distance is L. And I'm going to rearrange this. This is going to be delta prime minus L minus T naught. But that's equal to what did I do? Minus this is delta prime minus L minus T naught. So this is going to be, what have I done? This is delta prime minus that guy is delta prime minus L minus T naught, plus T naught. Okay, so this is equal to delta prime plus T naught. So therefore, we see the definition of A that I just erased. Oh, no, not yet, not yet. So what do we have? We have dp x naught prime is greater than or equal to delta prime plus T naught. Let's call this 4. Okay, so now look at the curve from P to x naught prime that goes from P to gamma of T naught along gamma, along the geodesic gamma. And then from gamma of T naught to x naught prime along a geodesic ray has length T naught plus delta prime. Let's look at this picture, right? I'm saying is if you go along this curve here, this is the point gamma of T naught. So this yellow curve has length T naught. And then you go straight to x naught along the geodesic ray, right? So this is the image of the straight ray in the exponential map. This has distance delta prime because that's the geodesic sphere of radius delta prime. So this yellow curve, which looks broken in my picture, has length T naught plus delta prime. And what we showed is that the distance is at least delta prime plus T naught. But now I found a curve with exactly this length. That means the distance is that. So hence, the distance from P to x naught prime is exactly T naught plus delta prime. So the curve that I just described, which looks broken in the picture, is a minimizing curve. So it's a geodesic. So this broken curve is minimizing, hence a geodesic, and hence not broken at all. I.e., if I call this part alpha, let's call it here and then along the geodesic ray alpha, that really means that the derivative, the velocity of gamma at T naught is equal to the velocity of this curve alpha times 0, right? So they really piece together. So by uniqueness of the ODE theorem, x naught prime is actually gamma of T naught plus delta prime. This yellow curve is not broken. X naught prime really is here, and the distance, this x naught prime is gamma at T naught plus delta prime. Okay, so we've got this equation. Which one did I call star? L minus T naught. So I guess I didn't need to number this because I'm just using it here. So then by the above and equation 3, I can erase the picture now. I don't need it anymore. What do we get? we get L minus T naught. This is equation 3 I'm rewriting. It says L minus T naught is delta prime plus D of X naught prime Q, but that's equal to delta prime plus, what is this? We just showed that this is gamma of T naught plus delta prime Q. So I can rearrange this to show that D of gamma of T naught plus delta prime Q is equal to L minus T naught plus delta prime. But that implies that T naught plus delta prime is in the set A, and that's what we wanted to show. Let me make a remark. That we've actually proved something a little bit more general. We're not going to be using it in that generality, but we actually, all we used was that the geodesics emanating from P were defined for all time. So in fact, we proved a slightly more general statement. If XP is defined for all T in R, for all V in TPM, then there exists a minimizing geodesic from P to Q for all Q. Okay, and if you think about how we proved it, we said, well, think about which one it would have to be. If it's going to be a minimizing geodesic from P to Q, then if you only go a little bit away, then it's going to have to hit that geodesic sphere at the point which is closest to Q, or at a point which is closest to Q, right? And then we know what the geodesic should be, and we're told it's defined for all time. We just have to show that it actually does hit Q like we expect it to. Okay, yep. That's how we defined the geodesic, right? X naught was a point on S, which was closest to Q. And then X naught was XP of TV, and we used that V to get the geodesic. So I have to go back and think about it. Let me think about it. I'm sure we have used it somewhere. It's not immediately obvious to me. Okay. Good. So the way that Do Carmo proves the Hopf-Rhino theorem, he writes down. Oh, sorry. Go ahead. Yeah, it's the same as before, right? Because if it does, then we know.
Could you repeat the question?
Yeah, sorry. The question was, did we have to assume that delta prime was small enough so that the ball of radius delta prime centered at gamma of T naught still didn't contain Q? And the answer is, yeah, that's right. And we can, the assumption is that gamma of T naught is not equal to Q. If it was, we would be finished, right? And therefore we can choose delta prime small enough so that it doesn't contain Q. That's right.
Just a small comment. You said it's a more general statement, but in fact, it's really kind of a special case because XP is not defined.
Yeah, so what I'm saying is, if you had a Riemannian manifold and you only knew that at one particular point P, XP is defined on all of that tangent space TPM. then any other point in the manifold can be joined to P by a minimizing geodesic, right? But let's say for some other point, P tilde, X P tilde might not be defined for all vectors in T P tilde of M, then we might not be able to join P tilde to any point by a minimizing geodesic. I assumed it was geodesically complete, which meant XP was defined on all of TPM for all P, right? But all I proved was, all I needed to get a geodesic from P to Q was that XP was defined for all TPM.
I see. So you're saying this is true even if M is not geodesically complete.
Yeah, all we need in order to join P to Q by a minimizing geodesic, we just need XP to be defined for all tangent vectors. That's right. Okay. So what I was going to say is that in Del Carmo's book, now we're going to do the Hopf-Rhino theorem. He says he lists 5 statements A through E. He says they're equivalent, and then he says any of these imply F, another statement. Okay, I didn't like the way he presented it, so this is his statement F. Okay, we're going to see that his A through E are all equivalent, and they imply F. So they imply the statement that we just proved. Also, one of his statements, two of his statements A through E are true by definition. His A and his E are the same. Okay, so let's state the theorem. This is the Hopf-Rhino theorem. So let MG be Riemannian, and the following are equivalent. First of all, G is geodesically complete. I.e., for all P in M, XP is defined on all of TPM. So this is what Del Carmo calls, when he calls one of these A and one of these D, but this was the definition of geodesically complete, so it doesn't make sense to do that. B, closed and bounded subsets are compact. Right now, a priori on a manifold, it's just a topological space. You don't have a notion of bounded. But now that we've shown that the metric makes it a metric space, we know what bounded means, right? And we saw that topology is the same. C says,
what have you written after let MG be Riemannian? What is that?
The following, TFAE means the following are equivalent.
Ah, thank you.
The following are equivalent. M is complete as a metric space. And finally, D is there exists a sequence of compact subsets Kj in M which are increasing. Kj is contained in Kj plus 1, such that if Qj is not in Kj, then for all j, then the distance from P to Qj goes to infinity as j goes to infinity. So in other words, we can find a nested sequence of compact sets. We can exhaust the manifold by this increasing sequence of compact sets, such that if we choose a point for each positive integer j, if we choose a point which is not in Kj, then it's not in all the ones before it either. Then for any P, the distances, these points go to the distance from any point P to these Qj's goes to infinity. Okay, these points are getting further and further apart. Okay, so the important, I mean, we're going to be using these later in the term, but the really important thing is that A is equivalent to C. That's the sort of guts of this theorem. Yep. No, they're getting bigger. Sorry. Oh, sorry. And union from j equals 1 to infinity of kj equals m. It's an exhaustion. What is the concern? Yeah. Oh, sorry. I said not, but I didn't write. Obviously, yeah. I wanted to be, I said it's not in kj, so it's not in any of the previous ones. Okay. Yeah, sometimes, we say the right thing, we write something else. Okay. Good. So the important thing about this is that A is equivalent to C. So geodesically complete, the metric is geodesically complete if and only if the metric space you get is complete. Okay, and because of this theorem, because these are the same concept, we're just going to say complete, right? We're going to say a metric is complete. That means it's geodesically complete and it's equivalent to the metric space distance function you get, makes it into a complete metric space. Okay, let's prove this. We're going to use the previous proposition. I'm not going to prove all of it. In fact, the equivalence of B and D that's just an exercise in metric space topology. I'll leave that for you. But let's start. So A implies B. So we're assuming it's geodesically complete, and we want to show that any closed and bounded set must be compact. So let A be closed and bounded. So there exists B, a metric ball. Let's write B is the set of all points Q in M, such that the distance from Q to P is less than or equal to capital R, a closed metric ball, such that A is contained in B. Okay, this is because A is bounded. Okay, but by the previous proposition, maybe I called it a theorem, I don't remember, one we just proved, we know that B is contained in XP of BL0 bar for some L. And this is because if Q is in B, with the distance, then the distance from P to Q is less, sorry, not, this should be L. If Q is in B, the distance from P to Q is less than or equal to L. So there exists a geodesic gamma with gamma of 0 equals P and gamma of L equals Q, a normalized geodesic. Okay, so that means so Q is in XP of BL0 bar. Okay, so that's why this is true. Okay, but this is compact, the closed ball in the tangent space, and that's continuous. So this is compact. Okay, let me write. I'm out of room, so let's write it over here. But BL0 bar is compact in TPM. So XP, this is the continuous image. This is compact in M. And then B A is contained in B, which is contained in here, is a closed subset of a compact set, hence compact. Okay, so I used here's where I use the closedness of A, and I use the boundedness of A over there. But before we continue with the proof, it's very important to notice the following. There was some P here. This is for some, I could make this any P, right? So this proof that A implies B, because it's bounded, it's contained in some ball. I can make that ball any ball I want. I can center that ball anywhere I want. The radius might change, right? But P was kind of arbitrary here. Any bounded set is contained in some sufficiently large closed metric ball centered at any point you want. Okay, so all I really needed was that the geodesics were defined for all time starting at P, the one starting at some point P. Let me make that as an aside here, and I'll emphasize it when we're finished the proof. So note, aside, to prove A implies B, we only needed XP defined on all of TPM for some P. And then that works. Okay, all the closed bounded sets are compact. Okay, so now let's prove B implies C. Yep. This one? No, I mean, sometimes they will be, but it doesn't matter, right? The point is, if you have a point with distance L, oh wait, let me see. Is it the same? They don't have to be the same. No, I think they are the same. These are, yeah, I think they're the same. We don't need that, but they're the same. Okay. So now let's prove B implies C. So we're assuming that all closed and bounded sets are compact. We want to show that it's complete as a metric space. So let PK be a Cauchy sequence in this metric space. We need to show that it converges. That's what complete means. Let A be the set of all points in this sequence. This is bounded because it's a Cauchy sequence. So its closure, A bar, is a closed and bounded subset. So it's an easy exercise to show that the closure of a bounded thing is bounded in a metric space. Hence, by B is compact. So PK is a sequence in the compact set A bar. This implies there exists a convergent subsequence because a compact set is sequentially compact. Convergent subsequence, but PK is Cauchy, so PK converges. Right? If you have a Cauchy sequence that has a convergent subsequence, then that sequence converges and the limit is equal to the limit of that convergent subsequence. Okay, so so B implies C. That's just metric space theory, right? That doesn't use any geometry. C implies D. So C is that the metric space is complete, and no, sorry, I want to do C implies A. Right, so this is suppose MD is complete, we want to show that the metric is geodesically complete. Okay, so this is the interesting part. So suppose not, then there exists a geodesic gamma with bound loss of generality normalized. We'll just reparameterize by arc length, such that gamma is defined on 0 T naught, but not at T naught. That's what it means to not be geodesically complete. There's some geodesic whose domain of definition is not all of R. I can take the problem point to be positive without loss of generality because I can change the direction if I want to. So let's let TK be a sequence in 0 T naught converging to T naught. And let epsilon be positive. There exists some n such that if k and L are at least n, then Tk minus TL is less than epsilon because this sequence converges, so it's Cauchy. But then the distance from gamma of Tk to gamma of TL, this is less than or equal to Tk minus TL, which is less than epsilon if k and L are at least n. And the reason for this is because this is a normalized geodesic. Right? So the distance between these 2 points is certainly going to be less than or equal to the length of gamma from here to here, because gamma is one curve from here to here, but the parameter is arc length. So the length of gamma from gamma of Tk to gamma of TL is exactly Tk minus TL, whichever one's bigger, right? So that's true. So hence, gamma of Tk is a Cauchy sequence in M. And we're assuming that M is complete, right? So gamma of Tk converges to some P naught since MD is complete. That means that the limit as k goes to infinity of gamma of Tk is some P naught. Now, we have to get our contradiction. This is the first place I think we're going to actually use, after chapter 3, we're going to use totally normal neighborhoods. And I did go through the rest of the book, and there will be one point where we're going to use geodesically convex neighborhoods later in the course. So let's let W delta be a totally normal neighborhood of P naught. So remember what that means. That means that W is contained in the delta normal ball of each of its points. Right. So maybe let me write it more accurately. XQ of B delta 0 for all Q and W. And we saw that we can do that. So choose n tilde, a natural number, such that k and L, at least n tilde, implies gamma Tk, gamma TL are in W. And of course, we can do that because W is an open neighborhood of P naught, and these gamma of TKs are converging to P naught. Then, since this is a totally normal neighborhood, there exists a unique geodesic beta whose length is less than delta, joining gamma of tk to gamma of TL. Right, because that's what the property of a totally normal neighborhood is. If I take any 2 points in there, there's a unique minimizing geodesic joining them, and its length is less than this delta, this parameter for the totally normal neighborhood. So, and it's clear that beta agrees or coincides with gamma whenever both are defined. And that's by the uniqueness of the ODE theorem. Right, so let me draw a picture. Gamma of TK, gamma of TL. Everything here is happening inside W. Let's say K is before, TK is before TL. So this is gamma. And I have beta. And beta is defined in this whole neighborhood. So that's right. So since X gamma TK is a diffeomorphism on B delta 0, right? That's because gamma of TK is in W, right? So X of gamma of TK well, it's what I wrote down over there, right? And let me just write it again. X gamma of TK B delta 0 contains W. The geodesic, this geodesic beta extends gamma past T naught. Because we've lost it now, but the TKs converge to T naught, right? So let's see. It should be looks like I'm missing a couple of details here, right? This beta exists, and it's we can follow this. That's right. We can follow beta for length delta, right? But because what am I doing? Beta joining. So gamma is coming from here, gamma of 0, and the TKs are going to T naught, and the gamma of TKs are going to P naught, and P naught is somewhere in here. What am I doing? P naught. That's right. P naught is in W. I've done something wrong. I can't see it right now. I want to argue that this beta extends gamma past T naught, right? If we do that, then we're done. But if it's obvious to one of you, tell me. Otherwise, I'll figure it out after, and I'll post it on Piazza. Sorry about that. It should all be there on the board. I just don't see it right now. Okay, so this was C implies A. Okay, and I'll leave B is equivalent to D as an exercise in metric space topology. It's easy to do, so I'll leave that for you. But let me make a remark. And this goes to the aside we had earlier. Remember, I said that to prove that A implies B, all I really needed was that XP was defined for all TPM for some P, right? Then I proved that B was true. Then I proved that C was true. Then I proved that A was true. But A is that it's geodesically complete. So we showed that A for some P implies B, which implies C, which implies A for any P. So in other words, this this fact, which seemed to be more general, sorry, you seem to be weaker, that we're saying the exponential map only exists for all vectors TPM at some P, actually implies that it's true for all P. So we've shown if XP is defined for all V in TPM for some, if for some P in M, this is defined for all TPM, then for all Q, XQ is defined on all of TQM. Defined on all of TPM. Okay, so it looked like we had proved something more general, but we haven't. Yeah. Yeah, that's what I want to do. And it's yeah, but I want to know why. So the comment was to how to fix this gap that I have here. And we're taking, so we take gamma up to TL, and then we want to take beta after, right? But I want to prove that beta goes longer than yeah, that's right. It has to exist for some small time. In fact, it exists everywhere in this W, in this totally normal neighborhood. But how do I know that? And it has length, it has some length. How do I know I get to? It's because I can make, that's right. It's because I can make the T, you're right. So this is the gap. So how do I know I can extend it? Well, beta exists for some finite amount of time past TL, because it's a geodesic going through T, gamma of TL. So it exists for some finite amount of time. And now I just take the T's close enough to T naught, so that the gamma of TKs are close enough to P naught, so that I know that this is going to now extend past T naught. Does that make sense? There exists some epsilon positive such that beta is defined at least up to TL plus epsilon. Okay, and now we just want to choose the T's close enough, choose L sufficiently large so that TL minus T naught is less than epsilon. And then that means I can actually go further than T naught. T naught was the limit of the T's. Yeah. So the hypothesis was that gamma is defined on 0 T naught, but not at T naught. But I'm saying it is because I can make these TLs as close to T naught as I want. And I know that there, if I fix, and in fact, that's the point, that the uniform time of existence from the ODE theorem it's uniform for all initial data in some open set, right? So in this open set, that's what it is. That's what delta is, right? So it's a uniformly normal neighborhood. So it contains for any point in here, it's contained in the ball centered at that. For any Q and W, W is contained in the ball of radius delta centered at Q. Okay, yeah. So this delta, this epsilon I wrote here should be delta, right? So I'm saying for any point in this W, we know that if you take a tangent vector at that point, the geodesic with that initial point and that initial a unit tangent vector will exist at least for time delta. Okay, so now if you just take the TLs to be close enough to T naught that they're less than distance delta away, you follow gamma up to TL for L sufficiently large so that TL is within distance delta of or let's say delta over 2 of T naught. And that means now I follow beta, and I can follow beta at least for time delta up to time less than delta, and that's going to pass T naught. Oh, and you want to go the other way. Yeah, that's okay. So the comment is we can also take geodesics from gamma of T naught. That's right. So you're right. So we can gamma, well, there is no gamma of T naught. You mean P naught. Right. We can take, that's right. We can take a geodesic from P naught to gamma of TL because they're both in W. That's right. And then you argue that by uniqueness, they patch up together. That's right. That's another way. Good. Okay. How are we doing on? Oh, we're good. So that's the Hopf-Rhino theorem. Some corollaries or a corollary. And then another comment. Corollary. Let M be a compact manifold. Then any Riemannian metric G on M is complete. And by complete now, I mean geodesically complete because that's equivalent to the metric space distance function, making it into a complete metric space. And the proof is a compact metric space is complete. This is basic metric space theory, right? So you put any Riemannian metric on G that makes it into a metric space, inducing the same topology. So it's compact metric space, so it's complete. Therefore, by Hopf-Rhino theorem, it's geodesically complete. Okay, so any compact manifold, any metric on it will be complete. So the sphere, for example, we could have known after this theorem that the geodesics have to be defined for all time. The only way you can find a non-complete metric is on a non-compact manifold. So incomplete Riemannian metrics can only exist on non-compact manifolds. By the way, before I say more here, for those of you who know that you can obtain geodesics by taking the flow of the geodesic vector field on the total space of the tangent bundle, right? That's not enough to give you this, right? Because you know that the flow of any vector field on a compact manifold is always complete. It always exists for all time. But the geodesic vector field is a vector field on the tangent bundle, and that's never compact, right? So the fact that that on a compact manifold, the geodesics exist for all time is this non-trivial thing we just proved, right? You can't use the fact that the flow of a vector field on a compact manifold is complete. Okay, and let me make another remark. So if some of you are looking at Lee's book on Riemannian geometry, which is a good book, I have both editions, but I've never looked at the second edition. First edition, the second edition is like 3 times the length of the first edition. And in the first edition, he has a mistake, which he corrects in the second edition. So we've shown that complete implies any 2 points can be joined by a minimizing geodesic. And this is, of course, not in general unique. Right? In the first edition of Lee's Riemannian geometry, he says that this is an if and only if. Okay, but it's not. And it's easy to see that it's not. This is not an if and only if. So here's an example. Let's just take the upper half plane in R2. This is our with the Euclidean metric. So that's an open subset of R2. We restrict the Euclidean metric, flat metric there. And this clearly has the property that any 2 points can be joined by a minimizing geodesic. In fact, by a unique one, because we know that the straight line between 2 points here is the geodesic, and for the flat metric. Okay, so this has, let's call this A and this B. This has property B, but it's not complete, because you can see right away this geodesic blows up in finite time. Right? The geodesics, once they hit the wall that I've created, I've removed the rest of the manifold. They don't exist after that. So there's an example of a Riemannian manifold where any 2 points can be connected by a minimizing geodesic, and here it's even unique, but it's still not complete. And the other example you should bear in mind is, let's say if you remove a point, it's not true that any 2 points can be joined by a minimizing geodesic, because if I took these 2 points, the geodesic you want is this one, but this one isn't in my manifold because I removed that point. And then you can see that there's going to be curves whose length is this close to this length, this distance as I want, but there's not going to be a curve with that length joining those 2 points. Okay, so this one is not complete and doesn't have A or B. This one has B, but doesn't have A. Yeah. If it's compact, it's definitely complete. So now you're saying if it's compact without boundary and any 2 points can be joined by minimizing geodesic, then does it? Well, it's a moot. Yeah, it's already complete. Yeah. So you see what I've done here is I've sort of taken complete things and I removed bits of it, right? So you could. I don't think it always has to be like that. You could find examples of Riemannian manifolds that are incomplete, where you can't complete them. And an example is a cone. If you take a cone in R3 and you remove the vertex, okay, then you can show that's and give it the induced metric from R3. That's a Riemannian metric. It's not complete because some of the geodesics want to go into the vertex and it's not there. And if you add that point, it's no longer a smooth manifold. So if you want to be able to fix these kinds of things by adding points, you may lose the smoothness. You may have corners and things like that.
Question.
Yep.
You said the upper half plane was a counterexample because the geodesics could be infinitely long, but isn't it just because the x-axis is missing? So points approaching the x-axis don't converge to a point in the manifold?
Yeah, that's what I'm saying. So any geodesic, as long as it's not parallel to the x-axis, will hit the x-axis in finite time, okay. And that's not in my manifold. So that geodesic will not be defined for all time.
Well, I thought you were saying something about extending it, into infinity, like the length of it. But okay.
No, that's a different thing. Yeah, so there's going to be a question like that on assignment 3, but that's not what I'm saying here. Okay, so we have 10 minutes. I'm going to state the next theorem, and I'm going to leave the proof to Monday. So the next thing is the Cartan-Hadamard theorem, which De Carmo just calls the Hadamard theorem, but I think there are lots of people call it Cartan-Hadamard theorem. So most of our, I think for the rest of the term, we're going to want to work with complete Riemannian manifolds. Those are the nicest ones. And of course, any compact Riemannian manifold is complete, but some non-compact ones are as well. And so we're going to see that if we have a complete Riemannian manifold and we assume something about the local geometry, like the curvature, or something about geodesics or Jacobi fields, then we can sometimes obtain global topological consequences from that. Okay, so this is our first global theorem. And it's the following. Let MG be complete. Essentially, all of these theorems are going to need completeness as an assumption, at least. Simply connected. So hopefully you all know what simply connected means, topological. Means the fundamental group is trivial. With the sectional curvature non-positive for all P in M and for all two-dimensional subspaces of TPM. Okay, so this has non-positive sectional. Certainly doesn't have to be constant, right? This is never positive. Then the exponential map, which goes from TPM to M, this is a smooth map. We know it's defined on all of TPM because our assumption is that the manifold is complete. And this is a diffeomorphism. So in particular, M is diffeomorphic to Rn, right? Because TPM is just an n-dimensional real vector space. So as a manifold, it's diffeomorphic to Rn. So it says that if you have a complete Riemannian manifold, simply connected with non-positive sectional curvature, as a manifold, it's Rn. That's the only thing it can be. Okay, so let me state some, we're going to prove this next time. Let me just state a corollary. Corollary, if M is simply connected, but not diffeomorphic to Rn, but not diffeomorphic to Rn, then M does not admit any complete Riemannian metric of non-positive sectional curvature. Right? This is just the contrapositive, essentially the contrapositive of this, right? If it's simply connected but is not diffeomorphic to Rn, it can't have a complete metric of non-positive sectional curvature, because if it did, it would be diffeomorphic to Rn. So in particular, if M is simply connected and compact, then any Riemannian metric G on M must have at least one point P in M and LP in TPM two-dimensional subspace, such that the sectional curvature at that point in that two-dimensional subspace is positive. And that's because If it's compact, it's certainly not diffeomorphic to Rn. And any Riemannian metric on a compact manifold is complete. Okay, so on any compact, simply connected Riemannian manifold, you can't have any metric will have to have positive sectional curvature somewhere, right? At some point and for some two plane. So in particular, Sn is simply connected for n at least 2. So any, and it's compact, so any metric on Sn n at least 2 has positive sectional curvature somewhere. And of course, the round metric on Sn has constant positive sectional curvature. That's the nicest one. But you can find a metric on Sn where n is at least 2, where it's always non-positive. By the way, it doesn't work for S1. S1 is flat, right? The curvature is 0 everywhere. Okay, so it doesn't make sense for me to start it now because I have 4 minutes. There's no way I can do anything. We're going to be using Jacobi fields and conjugate points to prove this. Yeah, so we're going to break it up into a couple of preliminary technical lemmas. One is an application of Jacobi fields. So let me just say in words, the first thing we're going to show is that if it's complete and non-positive sectional, if we just have these two assumptions, then every point has no conjugate points to it. The conjugate locus of any point is empty. Okay, so there are no Jacobi fields which are non-trivial, which vanish at 2 points. Okay, that's one lemma using the Jacobi equation, properties of Jacobi fields. Then we're going to prove that if the metric is complete and we have a local diffeomorphism between two manifolds, well, I'm not going to write it down, but we're going to prove that under some technical hypotheses, you can conclude that a map between two manifolds is actually a covering map. And we're going to apply that lemma. That lemma is of independent interest, which we'll use again later in the course. But we're going to apply that lemma to this case, because if you have a covering map between two manifolds and the first one's simply connected, then it has to be an homeomorphism. Okay, so I'm gonna state some facts about covering spaces and things like that on Monday. So on Monday we'll prove this theorem. It'll probably take about half the lecture, and then we're going to move on to talk about constant sectional curvature metrics more generally in chapter 8. Okay? And then after that, chapter 9 is about variational methods, so thinking about geodesics as critical points for the volume functional or the energy functional. Okay, that's the plan, and I will get you back assignment 1, I think by Friday, and assignment 2 is due Tuesday.